let's give it another 1 minute, and then we'll formally start.
Sounds good.
Thanks. All right. Hi, everyone. Today is again another lecture on geometric deep learning. And the last time we talked about some basics about geometric graphs and invariant GNNs. So today we're going to hear from a more advanced topic, is particularly equivariant GNNs, from Simon Matisse, who's a PhD in University of Cambridge, who has a lot of expertise in doing geometric deep learning for molecular systems and AI for science. So he's also one of the leading authors of the phenomenal work called Hitchhiker Guide to Geometric GNN in Atomic Systems, which I already have everybody read as a reading assignment. So without further ado, let's welcome Simon.
Nice. Thank you, Go. Thank you for the invitation. Can you just confirm that you can hear me okay?
Yes, we can hear you.
And let me see if I can share my screen. I wonder if there's a way that I can... Oh, there we go. Can you see...
We're seeing your... yeah, we can
see my
see
lecture
it.
slides now?
Mm-hmm.
Does that work? Can you see this?
Yes, this is you're playing a video.
Yep,
okay.
I'm showing a video here.
Okay, sounds great. Yeah, that works.
Okay,
can
nice.
Everyone hear it clearly? Cool.
All right. In this case, please feel free to interrupt me anytime if something's unclear. We have roughly an hour, is that correct?
Yes, we have actually more than an hour, like 70 minutes about.
Okay, excellent. So what you see here on the screen behind me is a biological system. This is an enzyme called ATP synthase. And you can see a lot of molecules flying around. And this is what brought me originally in this field. So modeling molecules with the help of artificial intelligence in order to ultimately design and create those molecules to use them in various applications, such as, for example, capturing carbon or other exciting opportunities like modeling new therapeutics. And that's also part of what Go has been involved in her postdoc at the Baker Lab, where I had the chance to meet her. Now, today I'll give you a brief introduction to geometric GNNs for 3D atomistic systems, such as the one you've just seen on the video. And this is largely based on this Hitchhiker's Guide that we wrote maybe a bit more than half a year back. And the Hitchhiker's Guide was really our attempt to help newcomers to the field to quickly get to the frontier of what's happening in geometric deep learning, particularly for 3D atomistic systems. And this was joint work with a couple of people, particularly Alexandre, Chaitanya, and Victor. And Chaitanya originally was planning to hold this guest lecture together with me, but unfortunately can't make it last minute due to another commitment. But you have his picture here, and he's also very willing to answer any questions. Okay. Was there a question? Just someone not muted. Okay. All right. Without further ado, let's go into it. I've highlighted two more resources if you find this topic interesting. There's a great book, Geometric Deep Learning, like a proto book written by Michael Bronstein and others, that you can find under this website. And the University of Amsterdam also has excellent resources and tutorial notebooks where you can see some of these architectures in action. So this is if you want to learn more. And I'll share the slides later if you get, and then you can share them with the students.
Thank you so much.
Now, I personally work on building AI tools for biology, particularly in protein engineering and protein design. And so I'm essentially trying to give evolution a leg up with the help of AI. And so you might ask, how does designing and engineering proteins relate to geometric deep learning and geometric deep learning in 3D? And for this, I want to briefly show you what a protein looks like. And what you can see here is a string of amino acids. So one of these blocks here is an amino acid. You can see there's various types. You see a tyrosine here in pink. You see a lysine in blue. And these amino acids can be described individually through essentially as a point cloud of atoms, so a 3D coordinate for every single atom, or they can be described in a more coarse-grained way, where you have a 3D position for the overall location of the amino acid and a reference frame that tells you the orientation of the amino acid as a rigid body. And the way we obtain these pictures is most often through what's called X-ray crystallography. So what happens is a biologist in the lab essentially puts together a couple of chemicals with the protein of interest and tries to get it to crystallize. If they do manage to get it to crystallize, they will drive it to a facility like this one. This is the Diamond Light Source in the UK. And in there, you have essentially a huge ring that accelerates electrons very, very quickly. And when you accelerate electrons and you move them on a circular path, they emit X-rays, so just very high energetic photons. And you can see these different beam lines here. And what you do is you hold your crystal into one of those beam lines. And what happens is your X-ray that comes in on this side here will diffract in a very peculiar pattern. And the pattern that you see looks a little bit like this. And you can then use this pattern to do an inverse Fourier transform to get something like a density map. So this looks like this. And then what you would do is you would fit atomic coordinates. You would say, this one here looks like an aromatic ring. So, maybe it's this or that residue. And so I will, or this maybe looks like a proline, so I will put a carbon and a nitrogen and so on in there. And this is how you end up with a protein structure here shown with the secondary structure kind of visualized. So this is how we obtain these structures, and that has historically taken between a couple of weeks to a few years, depending on the target, how hard or easy it is to crystallize. And geometric deep learning, among others, has really helped us kind of catalyze a revolution in biology and in AI in biology. And you can see here, this plot is the performance on a benchmark for protein structure prediction. And what you see is AlphaFold 2 in particular massively improving upon previous years. And this is also the first time a essentially invariant architecture, geometric deep learning, has been used in CASP, so in this protein competition. And if you've watched the news, you will have seen that this particular use of AI in the sciences was awarded just this year, a couple of weeks back, I think 2 weeks back, with the Nobel Prize in Chemistry. And so this is to motivate you a little bit that geometric deep learning has a short but strong history in protein science. And it's really catalyzed what we've been able to do. And this is, I think, one of the reasons to be very excited about it. And so ultimately, when we look at this structure that we get from X-ray crystallography, once we've put the atoms in, is a point cloud that looks like this. And there are various ways that we can featureize it or display it. So at the bottom, you can see we can connect these atoms together with the bonds that are usually covalently connected. And then you get the picture on the left-hand side on the bottom. In the middle, you see these kind of ribbon-like structures. So this is just a way of visualizing this point cloud in terms of secondary structure organization. And also another way of representing it would be as a surface in 3D. So there's not just a point cloud way, but there's many different ways to represent protein structures in 3D. And what all of them have in common is that no matter which way you look at it and which way you essentially represent your structure, the fundamental properties of that structure, what you would observe in an experiment in the lab, are unchanged, right? The ground state energy of this structure is always the same, no matter whether I look at it from here or from there. And this is the idea of invariance. And the idea of equivariance is that if I, for example, were to measure the forces in this structure that are exerted by the atoms on each other, then if I just rotate the structure, these forces would rotate accordingly. And that is the idea of equivariance. Equi just means the same way. Variance means to change and vary, and equi means in the same way. And so equivariance would mean those forces would just change in the same way that I changed the way I look at the structure. So yeah, these are different ways of representing proteins. And the point I want to make here is just that all of these benefit from the principle of, or all of these exhibit these symmetries in 3D space. And so accordingly, they all benefit from modeling with invariance or equivariance in mind. Now, this I've already said, if we go back and coarse grain the structure, so even if we weren't to work exactly on the individual atom level, so on the 3D coordinates of the atom, but if we were to work on a more coarse grained level, so say we collapse all of these blue atoms of lysine here into a single atom, and we just say the direction, the major direction that it's pointing at is going to be our first fundamental, like our x-axis in the local coordinate frame. And then we point our y-axis along the backbone, so this gray line that you see here. And then we get the third direction through Gram-Schmidt orthogonalization, or essentially just the third rectangular direction that you can get in 3D. Then I can model it with fewer parameters than 3D coordinates for all atoms, but I will still have symmetries. And now I will be modeling in a combination of R3 for the XYZ coordinates and SO3. And those are the SO3 is just the group of rotations for the reference frame. And so no matter whether I coarse grain the structures or whether I work on the full atomistic level, and no matter whether I work on individual atoms, bonded graphs, or surfaces, the principle of symmetry pervades all of these because the fundamental properties of these systems don't change depending on the way I decide to look at it. And so this is why, to answer my initial question to myself, why, when you do protein engineering and protein design, why do you come in contact with geometric deep learning? It's because we often work with structures, because structures tell us a lot about how proteins work and function. And there's a lot of tasks we want to do with structures in protein science. And accordingly, many of these tasks benefit from modeling with symmetry in mind. And so this is why, for me as someone who's working on proteins, I'm spending a lot of time thinking about symmetries, or spent a lot of time thinking about symmetries in the past. Now, to just give you 3 applications in proteins in particular, you can use, when you have these type of geometric graphs, and I'll refer to any kind of set of coordinates, whether they're coarse-grained or fully atomistic in 3D spaces, geometric graphs from now on. When you have a geometric graph, you can solve a variety of prediction problems. So what are the functional properties that are related to this enzyme or to this protein? What are the, for example, binding affinities between 2 of these graphs if I put them together? But you can also capture generative tasks. So, you might have a distribution of proteins of interest, so a distribution of 3D point clouds or 3D graphs of interest. And now you want to generate more of these proteins that adhere to specific constraints. So for example, they might be shaped like a hinge so that you can have a hinge type motion or so on. And that's a lot of what happens in David Baker's lab, for example. And so you'd have generative models that also now work with geometric graph neural networks. And then finally, we also know that a single structure is not actually what happens in reality. When you think back to the video I showed you at the very beginning, you saw a lot of jiggling motion. And so these structures actually change as they undergo transformations. And if we wanted to model essentially the video of what happens in a human body or in a reaction, we need to do what's called molecular dynamics. So we need to essentially update the structure based on forces. And for doing these sort of iterative simulations, geometric GNNs are also very widely used in practice. And so this gives you a couple of applications. And you now might be asking, I've talked a lot about proteins and geometric deep learning in 3D in proteins. Is there anything beyond equivariance? And this is just one slide to show you. There are many other applications. So proteins is one of the molecules benefiting from that. Quite naturally, you'd expect small molecules or DNA, RNA to also benefit from this. There's also lots of work on crystals. Also, in many cases for materials applications, for example, at Meta, there's quite a big tradition of this with the Open Catalyst team. But even beyond atomistic sciences or molecular kind of applications, geometric graphs find applications in transport and logistics. So for example, a 2D graph or a graph that is in 2D, but not actually in a Euclidean 2D space, but a 2D sphere. That would be if you had a transport network on the globe, so the sphere of the Earth. But you also see it in robotic navigation, 3D computer vision, etc. So these are a couple of other application areas beyond molecular sciences. So hopefully I've kind of got you interested in some of the tasks that kind of happen down the line with geometric graph neural networks. Now the question is, what are we actually trying to achieve when we model these systems, and how can we try to do that? And the main idea is that in machine learning, we always essentially parameterize a function with weights, and then we try to tune those weights based on a set of data in order to represent, in order to then, when we put a new data point in, to get a prediction on what the value for that data point would be. And so we parameterize this function. I'm just going to call it f. That might be a neural network, but it might be also something, an ansatz you make based on some physical knowledge that you have. Nowadays, most often it'd be a deep neural network. And then really what we're saying with invariance is, and you see potential energy landscape here, no matter whether I rotate my molecule or not, I want it to have the same energy. And with equivariance, no matter whether I rotate my molecule or not, the relative directions of these forces here, in which these atoms get pushed and pulled, should change accordingly. So that was equivariance, as I explained it briefly. And to give you a brief overview of how this has been achieved and kind of how people have thought about doing this, I can now go and say, okay, I want this function to always be equivariant. I want to make it impossible for this function to actually be sensitive to the orientation of the input that I give it. And that's when we arrive at what I call exact equivariance. So we really build the symmetry into the architecture. And there are, broadly speaking, two approaches. The first approach is what I like to call reference frame approach. And the idea is, if I have this structure here and this structure, what would be one way I could make it insensitive to the way it's rotated? And one way I could do that is if I had a function that would always give me a coordinate system. And the coordinate system, for example, would always point with the x-axis along the red atom, and with the y-axis along or in the plane of the blue atoms. Then I could always, even if I rotate the structure, assign the same coordinate system also rotated, and now I would always describe it in the same way. And so this is what I call global reference frame approaches. And an example of that in the machine learning literature would be FEINET. And the challenge here is that you would need to come up with a function that gives you the same canonical reference frame, no matter what the original orientation of your system. And the way this can be done, or this is done in FANET based on the data, is to do a singular value decomposition. So to find the directions of major variation. And then you just say, my x-axis is going to be the first major direction of variation, the y-axis is the second, and the z-axis is the third. And then the challenge is, obviously, when you do a singular value decomposition, you get two signs out for the x and the y-axis. And because you have three directions, x, y, and z, you get 2 times 2 times 2, so 8 different possibilities of the signs of the coordinate systems. And so what they do in this particular paper is they just average over all those 8 combinations of all those possible choices of signs. And that makes the output exactly equivariant. So no matter what you put in, if I rotate it, I will get the same exact output because I will run it 8 times with all the 8 different ways I can assign the signs. The problem with a global reference frame approach, though, is if you were to do something like a molecular dynamics simulation, you would have atoms moving in and out. And so if you imagine your first principal component, your major direction of variation is along this axis. Now, if you change your point cloud slightly, that might drastically change the axis of variation, the major axis of variation. And so you get essentially non-differentiable flips, or essentially very large flips with even very small changes in the input structure. And so that's one of the drawbacks of a global reference frame approach. A local reference frame approach is the same fundamental idea. So I assign x, y, and z axes that I can canonically assign no matter where I am. But I do assign different x, y, z axes at every single atom. And that's what happens in AlphaFold. So if you go and read the supplementary of AlphaFold 2, if you're interested in this, I highly encourage you to do so because it's very well written and nicely explained. What they do is they use the protein architecture. So the backbone of the protein gives you a unique direction from left to right. There's a notion of a beginning and an end of a protein. And they use that to come up with reference frames at every single position. And then when they perform their attention mechanisms, what they do is they transform, if they do attention between one atom and another atom, they would transform this atom's features into the other reference frame by knowing how to rotate and translate these two reference frames. And so you'd have one reference frame at every single position. And I'm going over this a little bit more quickly because I will focus on a slightly different way of achieving equivariance for the rest of the lecture. But I just want to give you a quick idea that there is other ways. And so AlphaFold 2 obviously famously was a very successful application of equivariant neural networks. The problem with a local frame approach is you can't always assign local frames easily. Again, you need a procedure in order to canonically assign these reference frames. And for proteins, that's nice and easy because you have the backbone which gives you a unique direction. So from N to C terminus, from start to end. But for general molecules, imagine you're in a benzene ring. Which one is your starting direction? Which one's your ending direction? And so as soon as you have cycles in your structures, it gets much more difficult to define local reference frames. And that's one of the problems and drawbacks with local reference frames. And indeed, you'll find that AlphaFold 3 does not use reference frames anymore. So this was rough branch 1 of achieving equivariance. Branch 2 is to essentially do a counting on your features. And that's what Ge has already, I think, explained to you in the previous lecture. One way to achieve invariance would be to make sure that whatever you feed as features into your network is invariant to begin with. Because if it's invariant to begin with, no matter what I do to the input, will obviously be invariant by definition. And so what I get at the output will also be invariant to those transformations. And today, we'll talk a little bit more about equivariant features and how to achieve that. So I won't go into detail in this box for now. And then on the other side, on the flip side of kind of achieving equivariance is, what if we don't use that function that I showed you earlier, which in our case is often a deep neural network, and force it to be equivariant? But what if we have that as a learned emergent property as we train? And so this is the idea of approximate equivariance. So our architecture actually acquires the symmetry through training rather than through initial kind of predisposition by making it, forcing it to be equivariant. And the two main ways of doing that is by performing data augmentation. And that's actually what happens in AlphaFold 3, so the latest update to the AlphaFold saga. So you would just give the same structure rotated many different times, and you would just train for longer. And what you will then observe is that your weights start to adjust such that the function that you have, that you end up parameterizing after training is actually almost equivariant when you test for equivariance. The challenge obviously is when you go far out of domain, because then you have no guarantee anymore that your weights stay equivariant. So that's one of the challenges with a data augmentation approach. And then the second approach that allows you to achieve approximate equivariance is by adding equivariance terms or symmetry terms in the loss. So penalizing your network if it makes differences between this or that orientation. And there's very recent work. Rimal is one of the most recent and well-studied papers combining actually data augmentation with symmetry loss. And the focus of this talk for now will be on the feature accounting approaches, and particularly on equivariant features. But I will say something on the exact versus approximate equivariance question at the end of the lecture. And so this is a teaser for the epic battle between exact and approximate equivariance. So don't fall asleep on me, otherwise you might miss this discussion at the end. All right.
Sorry to interrupt, Simon. Do you mind if you hide your figures from the talk? I'm showing your video.
Oh, I see. Okay.
Yeah, but I think part of the slide is.
Oh, is obstructed. Okay, let's see. How do I do that?
And if there's any questions, feel free to raise your hand.
Is it better?
Hello, can you hear me? Yeah.
Yes, I can hear you. Yeah.
So, what do you think of that AlphaFold 3 has removed the IPA module, and it seems it doesn't consider the equivariance anymore.
Yeah.
For clean for the ins and achieve the absolute performance. How do you think? I'm not sure if equivariance is no longer important in geometric this kind of thing or not.
So we'll get to that in the end. So this is this teaser here. So I'll speak about this exact question at the end. Yeah, let me not answer it yet, to keep you on the hook and hopefully interested. And then we can have a discussion on this at the end. But thank you for the question. Any other question at this point? Sounds good. Okay. So some of the key takeaways, and don't worry if this doesn't make sense yet, at the end of the talk is you'll have a taxonomy of geometric GNN architectures, because most of the research in geometric GNNs has actually been in this equivariant feature approach, which is probably the most theory-rich, and papers in this space can get pretty complicated. And so this, at the end of this talk, my goal is that you'll be able to essentially categorize them according to different approaches and understand the main ideas, even if you don't understand all the details in those papers. And so you'll see essentially these three categories that we are using in the Hitchhiker's Guide: invariant GNNs, Cartesian equivariant, and spherical equivariant GNNs that capture most of the papers in that space. we'll also briefly at the end talk about unconstrained GNNs. And there's also a section in the Hitchhiker's Guide, although we do need to update that with some of the more recent work. And the second thing you'll go away with is categorizing what some of these approaches. So I've shown you that there's different ways of achieving equivariance. Why would you choose one over the other? And why have people worked on this approach, that approach? What have we learned about what some architectures can do that others cannot? And which things seem to be important for which problems? And so we usually categorize it or categorize architectures in this 3D grid where we talk about the tensor order, and I'll explain what this means. It will become evident over the course of the lecture, as well as the many-body body order of individual single layers, and then ultimately, of course, the depth. And so within this framework, you'll be able to understand essentially what functions can be represented by some networks that cannot be represented by others. So these are theoretical limits of geometric GNNs. Yeah, and I'll explain those terms as we go, as we learn them. Now, there's a very brief section on background graph neural networks and geometric graphs, but I think, Igor, you've already explained a lot of this, right?
Yeah, I think we covered this part.
Okay, excellent. So I can mostly skip this. Okay, excellent. So I'll breeze through this very quickly, then we have more time for the other parts. But so how can we get graphs? If we have a 3D point cloud, we can have smooth cutoffs, we can have long-range interactions, for example, if we have crystals, or we can have a complete graph. Anyone, what does that remind you of? What type of neural network architecture does that remind you of?
The answer transformers.
Transformers, excellent. Yeah, okay, nice. So you did do a good job, Ger. So this is essentially various ways of generating graphs, and the limit of a fully connected graph would simply be a transformer architecture or a transformer style connectivity. On graphs, we characterize them with an adjacency matrix and features. This is just normal graphs, and the important thing about graphs is that you would assign labels to different nodes, and so you need to be invariant to those labels, because those labels are just something we humans use in order to orient ourselves, but they're not actually having any physical underlying meaning. And so what normal graph neural networks do is they essentially proceed in two steps. There is a message creation step, well, 3 steps. There's a message creation step here, where essentially between each 2 nodes, I create a message from node I to node J. I aggregate all the messages around node I, and then I update the state of node I based on the messages, the aggregated message it has received. And so this aggregation and update, this aggregation in particular is what needs to be permutation invariant, because that's where the indices start to matter. And so that's, when you unroll it, you essentially get this computation graph. I won't go into these details since you've heard about these before. The difference in geometric graphs is that in addition to permutation, the permutation group, which gives you some notion of symmetry, we have a second group that acts, or actually 2 other groups, depending on how you want to slice it. And that is translations and rotations and reflections. And so our graph is now embedded in 3D space. And in the notation here, I'll be using x to denote coordinates and v to denote any other vector type features that might be attached to nodes. And s here just stands for scalar features. And so I might have various scalar features associated with a node, as well as a position and possibly vector features. And later on in the talk, we'll also talk a little bit about higher order tensorial features. And so these could correspond, for example, to velocities or forces, just to give you a physical idea of what these could be. And then the extra symmetry that we get by being in 3D space is that whether we rotate the structure or not, we need to rotate some of these features accordingly. Obviously, we know how positions and vectors rotate, and we already said that scalars are invariant. And translations similarly act by changing the positions, but not changing scalars or vectors that are associated with the graph. And so the whole game is now, how do we actually build something that respects both permutation and 3D rotation and translation symmetries. And usually we get rid of the translation symmetry by just centering the system in the center of mass. This is not the only trick. There is also tricks that if you go into some of the literature on geometric algebra, you'll see that you can go into what's called the projective algebra. And in that case, you can also encode affine transformations, so translations. But for the most part, you'll see almost all papers use a center of mass trick, where you center your point cloud at the center of mass, and through that remove that symmetry. And that's the same as the reference frame trick, essentially, just for this particular symmetry. But for 3D rotations, it's harder, because for 3D rotations, you would now actually come up with 3 directions of your reference frame. And so that's why the reference frame type approach is used very often for the translational degrees of freedom, but not so often for the rotational degrees of freedom. Now, let's go and characterize the design space of geometric GNNs that we can build that have these properties of permutation and 3D rotation, rototranslation symmetry. And we'll use these 3 axes, body order, as well as tensor order and depth. So how can we make these 3 axes essentially are meant as a way of talking about how we can make a architecture more powerful than another. And so let's start with scalars. And Go has last time already talked about Schnet. And Schnet just says, okay, how can we get scalars from a point cloud? We just take the magnitudes of the distance vectors between the atomic coordinates. So I take xi minus xj, and I take the norm of that, and that will give me something that doesn't change upon rotations. And so this is great. This gives me essentially a pairwise feature because I have features that depend on nodes I and j. And so a general GNN architecture that does something like this could look like this. So F1 would be just any type of unconstrained featurization function. So this can just be a multi-layer perceptron, for example, including, say, layer norms and so on. Any scalar features you already have at node j at depth t of your network, as well as the distances between xi and xj. And you add that to the feature you already have at node I, and that will give you the scalar feature at that node at the next iteration. And what I'm hiding, obviously, here is I'm hiding all the feature dimensions. So these are boldface because they would have feature dimensions. So I could have multiple scalars at every position. Now, distances can be constraining, right? Because you could have a local environment, a graph which would be a complete straight line of 3 nodes, or you could have a graph which would be bent in a 90-degree angle. Those would have, possibly very different energies, but if you only look at the one-hop neighborhoods, and if you don't look at a fully connected graph, so if you don't look at a transformer-style architecture, which tends to be the case in a lot of atomistic applications because the number of atoms is just so large. And so the context for running a full transformer, which scales as O(n) squared, becomes challenging. And so that's one of the reasons why people would use graphs over transformers. So if you have, tens of thousands of atoms. And when you have that, when you have a line versus a 90-degree local neighborhood, then you could have them have the same distances, but different angles, right? And so another way to essentially deal with that and to make sure that I can distinguish these 2 environments would be to add angle features. And so far not so complicated. the next architecture kind of that went and built on Schnedt was saying, okay, you know, angles do matter, so let's add angles. And an angle would be a triplet. It would depend on 3 nodes, right? I need I, j, and k. I need an apex and 2 sides to actually define the angle. And in vector language, an angle would essentially just be corresponding to a dot product, which corresponds to scaled cosine of the angle. And so by introducing the norm of the distance vector as well as the scalar product between 2 different distance vectors of nodes, I can now reason about distances and angles in my local environments, and that makes me more expressive. And this is an example of what we call body order, because an angle would be a body order 3 feature, because we used 3 nodes in order to compute it in 1 layer. Now, what's the challenge with invariant networks? Any of you have an idea of kind of what the problems can be in invariant networks? Sorry?
It's not expressive enough.
It's not expressive enough. What is the answer?
It's not expressive enough, okay, yeah. And why could this be a problem? So, I mean, the equation's down here, but it's following the same exact pattern as before. So why can this be a problem? As you say, there can be a limit on the expressivity. And it turns out that actually, if you just keep increasing, you know, angles, dihedral angles, etc., there are always situations that you can create where you cannot distinguish 2 microenvironments unless you go to the full n-node body order. And so this is an example of 2 structures that you cannot distinguish based on distances and angles. So you see the distances between all types of nodes here is the same. So we've got, you know, gray node to the red nodes, to the yellow node, to the blue node. So all the distances are the same. And if you count the histogram of angles, because remember, because we are permutation invariant, we don't know from which node which angle came necessarily. And so, or from which node, if they are equally colored, which angle came. And so if you look at the histogram of angles, you will actually find that you cannot distinguish these 2 microenvironments purely based on distances and angles. And this is essentially relevant because if I can't distinguish them based on distances and angles, that means I would need to introduce higher order body order features in order to distinguish them. So what I could do is I could go and measure dihedral angles. A dihedral angle is an angle between planes or between essentially a quadruplet. But then I'll find, you know, that there's features that are not represented by quadruplets, so I need a quintuplet, and so on, and so on, and so on. And the problem with quadruplets and quintuplets is computing all distances ahead of time, that's fairly quick, that's n squared, right? Computing all triplets ahead of time, so all angles, that scales as n cubed. Computing dihedrals for everything, or even a constrained subset of nodes ahead of time, scales as n to the 4, and so on. And so you essentially get this combinatorial explosion of featurization at the start. So you need to essentially choose what body order you want to represent at the beginning. And if you then learn that it wasn't enough, you need to essentially retrain a new network with a higher body order, and you need to spend quite a bit of featurization at the beginning in order to compute all of those higher order terms. And so people really like when you can scale the expressivity of your architecture by just stacking more layers in deep learning, right? So how nice would it be if we could automatically create 2-body, 3-body, and so on features by stacking more layers? And that will be what equivariant architectures are innovating over as compared to invariant architectures. And the what that ultimately allows you to do is that you can transport orientational information from one part of the graph to another part of the graph and create these essentially non-local higher body order features. And so this is just a nice example from the Payne paper that shows why distances and angles, again, are not enough, and how you actually would need to transport information from this local microenvironment. So on a local microenvironment level, both of these would be an elbow bend of alpha degree. But I don't know how these two microenvironments are oriented with respect to each other. And in order to do that, I would need to have either a quadruplet feature, so knowing something about these 4 nodes, so essentially 4 hop neighborhoods, or I would need to pass along orientation information. And passing along orientation information brings us to equivariant graph neural networks. And this is just a cartoon illustration of why this is important. Obviously, you can tell this is a smiling face, but you don't tell that just by knowing there's a mouth, a nose, and 2 eyes. You also tell that by knowing how relative to each other they're positioned. And essentially, that's the problem. And so even though we could pre-compute many of these higher body order features, it scales poorly. And so we want something that will scale with depth. So let's start, passing on orientation information by keeping the vectors around. So keeping those coordinate vectors, and see if I can create those body order features, essentially angle type information, etc., by just computing with those vectors on the fly. So I have scalar features and now also vector features. And what I need to do is now I have 2 types of messages. I have a scalar message that we had before. So this is what Ger has told you last lecture. And I have a vector message that now also carries orientational information. And when I aggregate, I need to keep, obviously because scalars and vectors transform differently, I need to disentangle my scalars from my vectors. And so when I aggregate, I need to get out a scalar message as well as a vector message. And when I update accordingly, I need to update the scalar features and the vector features separately. And so what we're studying in the next couple of slides is different functions and approaches of how to define those. So this is what I said just a moment ago, so we can skip it. The scalar features need to be updated invariantly, but vector features need to be updated equivariantly. And so this brings us, we've talked about this body order before, this brings us on this second axis here in this graph or in this design space for geometric GNNs, because now we talk about what will come to be called the tensor order of features. And so for now, we're just dealing with scalars and vectors, but we'll see how that will generalize to more general tensors and where these tensors actually arise from or pop up. So the simplest architecture that essentially combines scalar and vector geometric information just says, okay, what sort of informations can I do with a scalar and a vector in order to still keep a vector? And what operations do you know between scalars and vectors? Sorry? Yep. And in particular, there's different types of multiplication. So there is the multiplication of a scalar with a vector, and that would just be a scaling operation, right? That's why it's called a scalar. There would also be the operation of, and I put this in air quotes, multiplying a vector with a vector. And that's not immediately defined, because if it were, then we'd be in what mathematically is called a field, right, where you know how to multiply entries. But a vector and a vector, by definition, don't have a notion of being multiplied. But we do have 2 different types of multiplication operation or multiplication type operations that you see. And that's the dot product. So I take a vector and a vector, and what I get out is not actually a vector, it's a scalar. And the other thing that you know is a vector product, a cross product. So if I take a vector and I do the cross product between them, or vector product, however you want to call it, I get another vector out that now points in the direction perpendicular to both of them. So I can now essentially incorporate these different types of multiplication rules and addition rules in order to take a set of vectors and create more vectors from them, and take a set of scalars and vectors and create more scalars and vectors from them. And so Payne basically just enumerates all the different possibilities that I can do. So the different possibilities would be scalar with a scalar, scalar with a vector, and then vector with a vector that goes to a scalar, and vector with a vector that goes to another vector, so a vector product. So I take these 4 different types of product, and I split my message up into all of those different types. And so in this particular case, Payne doesn't actually use cross products, but what they do is they essentially gate the vector features at every position with a new scalar that is obtained, and that depends on the scalars of the previous iteration at node j. And so what you're seeing is essentially this gating of vectors. And the reason I'm gating the vectors, and I'm not applying a ReLU or so, is that if I were to apply a ReLU, that would break equivariance. And an easy way to see this is, imagine you had the vector 1, 0, 0. If I apply a ReLU to that, right, as we would normally do, that would still remain 1, 0, 0. But what if I now rotated the positive 1 axis into the negative x-axis? Now my vector would be minus 1, 0, 0. And if I now apply a ReLU, it'd be all 0. And so I've lost information. And so really, we shouldn't be, in PyTorch, we shouldn't call things tensors, but we should call them lists of features. Because what distinguishes them is, what distinguishes a tensor and a list, kind of in physics language, is that a tensor has a well-defined transformation property under symmetries, whereas a list doesn't have any notion of necessarily transforming. And so we now, because we deal with things that have symmetries and we deal with things that are just plain features, we now need to disentangle the notion of a list, which is just a collection, so a collection of vectors, from a vector being a type of tensor, namely a thing that transforms under a given symmetry, namely rotation, in a specific way. And we can perform nonlinearities, so ReLU and so on, component-wise nonlinearities, on components of lists, but we cannot perform nonlinearities on components of physical tensors. So we can't do a nonlinearity on a geometric vector, essentially. And so if we extend this idea, or if we kind of abstract of what we've learned by looking at Payne and essentially these multiplication rules, the idea behind equivariant architectures is actually extremely simple. And the idea boils down to essentially doing accounting. So each feature has a type, and the type is what defines how it transforms. And if you have a mathematical background, you'll know the word type as representation. So this comes from representation theory. There's a whole branch of mathematics that talks about this. And a type would be a representation. So a scalar would be a particular representation of the SO3 symmetry group. And a vector would be a different type of representation. And in computer science language, it's just something that behaves differently, which is why we've opted to call it type rather than representation in the Hitchhiker's Guide. And I'll stick with the type name for the rest of the talk. So we have different features that now have different types. So scalars and vectors are 2 types that we know. And we also have addition rules. So we can add a scalar to a scalar. We can add a vector to a vector, but we cannot add a scalar to a vector. There's no notion of that. That obviously happens in like, again, when we're in Torchland, you would do broadcasting, but really what you're operating with is a list of features and not a geometric vector that has any notion of 3D space. And so you can do addition, and you have multiplication rules. So you can multiply a scalar with a scalar, and you get out a scalar. You can multiply a scalar with a vector, get a vector. You can multiply a vector and a vector, and get a scalar or a vector, depending on what type of multiplication you use. And everything we need to do now is we just need to keep track of, after performing a couple of operations, what's the output type, depending on the input types and addition or multiplication operations that we've done. And so this is everything. So if you understand this idea, which I think is really simple, I tried to ask ChatGPT to have someone doing accounting with geometry, geometric structures. If you get this idea, you get all of the complex architectures that will come below. And the only difference is what the types that they're using are and what multiplication rules that they're using are. Any questions at this point? All right, sounds good. What was that question?
No, I don't see any raised hand yet.
Okay, cool. I'll keep going. All right, so we defined a type, and it's defined by how it transforms. And we already know scalar and vector types. Are there any others, you might ask? You know, why would I even need to think about anything else? And so let me give you an example of another type. So what if I take the combination of components of a vector v and a vector w? So these are both just vectors in 3D space, or this generalizes to ND, but let's just keep with 3D. And I just create all the 9 combinations. And I can arrange them in a matrix. And when I look at how this object transforms, so when I write this as a matrix, and I look at how it transforms when I rotate my vector vi and my vector wj, then when you write it out, you'll find that this matrix actually transforms as Rm R transpose. And so we found an object that now transforms differently from a vector and transforms differently from a scalar. And so we've now, by definition, found a new type. And in component form, it will look like this. So this would be an object with 9 components, kind of like a scalar has 1 component, a vector has 3 components. This M object has 9 components. And this M object is actually called a rank 2 Cartesian tensor. And so rank corresponds to the number of indices. And the word tensor here means it is something where that transforms under symmetry operations. So again, I'm overloading the word tensor. I'm using it in a different way than it's used in machine learning typically, because in machine learning, typically tensor just means collection or list of. But here I mean to say transforms in a certain way. So we found a new type, and this is just visually displaying how I could arrange them. I can also, flatten and stack them, and I could, at every layer in my network, do an accounting of saying how many Cartesian tensors of rank 0, which is a scalar, I have, how many Cartesian tensors of rank 1, which is a vector, I have, Cartesian tensors of rank 2, and you get the idea. You can go down essentially up to infinite rank with these tensor components. And when I have a channel dimension, those would essentially just be stacked across the channel dimension. And so now I've introduced essentially another dimension, or if I flatten it, this would be how you would represent it in memory, right? You would essentially have pointers that tell you, this is where all my scalars are stored, this is where all my vectors are stored, this is where all my rank 2 tensors are stored, and so on. And by not mixing them arbitrarily, but mixing them with the multiplication rules and addition rules that we've discussed, you can always know what the output type is and slot it into the right position in memory. And by that, you can keep your architecture equivariant, because at every point in time, if you ask me, how does this feature transform that's in this channel, I can tell you exactly how that happens because I've slotted it in the correct place. And so when I look at kind of how they transform, this would be a 1-by-1 matrix, right? This would be the representation matrix of a rotation for scalars, and that would just be the identity because the scalar wouldn't change. The representation of rotations for a vector would just be the rotation itself, rotation matrix itself, and then these become more complicated, but the idea stays the same. So this would be a 9-by-9 matrix that corresponds to, if I were to represent these components as a matrix, left and right multiplication of R and R transpose. And so everything we need to do is just keeping track of how we sum them, and that we only sum essentially tensors of the same order, because how otherwise would you sum a 9-component list with a 3-component list? So sums can only happen between tensors of the same order, and products can happen between tensors of different order, and they will give us new types. So they will give us higher or lower types. And so that gives us, essentially an infinite zoo of types that we need to do accounting with. And so a natural question to ask is, okay, given kind of this setup, I can create a lot of different types. A, why would I want to do that? And B, what if I, wanted to actually characterize my architectures? What would be the most expressive architecture? How do I know whether I have all of the types? How do I know that I haven't missed any that I could still build? Is there any way of categorizing or systematizing those types? And turns out there is, and in representation theory, which is the mathematical theory of this, this would be called in mathematics. These are called so-called irreducible representations, and all of these are known. These are essentially your Lego blocks with which you could create any other type. So any type can be decomposed into those irreducible representations and can be composed off those irreducible representations. And for 3D symmetries, so rotations and reflections in 3D, all of these irreducible types are known, and they lead to the spherical harmonics. And that's why we call them here spherical tensors. And so sometimes you might have wondered, where do they pop out? This is the reason they pop out. So they are essentially just theoretically the linearly independent way of representing these representations. So this is essentially the cleanest way of writing types for rotations and translations. And this leads to a couple of famous architectures that you might have seen if you follow the molecular modeling space: tensor field networks and multi-atomic cluster expansion, MACE, which are used these days a lot in MD simulations. And so just to show you how one of these compositions would work, if I take my Cartesian tensor that we created before, so rank 2 Cartesian tensor, how can I decompose it into these spherical tensors, which are the fundamental Lego blocks? Well, if I take the trace of this matrix, so if I sum up the diagonal, that is actually guaranteed to not change when I multiply left and right with rotation matrices. And so this is invariant. So this would be corresponding to a scalar degree of freedom. When I can then also decompose the remaining off diagonals into an antisymmetric and a traceless symmetric part. And the antisymmetric part turns out to have 3 components. And obviously the other part would just be clear or already defined by these 3 top components through symmetry mirroring on the diagonal, because it's antisymmetric, so it changes sign. So bottom half is mirrored in sign with respect to the top half. And this turns out to actually correspond to a vector feature. So that would be an L equal to 1 feature. And then an example of a L equal to 2 feature would be this traceless symmetric component of that matrix. And so I can decompose this as a direct sum of a scalar component, a vector-like component, and a symmetric component. And the equations for this are written out in the Hitchhiker's Guide. So if you're really curious on kind of how to do that, it's a really instructive example in order to connect these two ways of thinking about it. In graphical language, we've always used kind of bluish colors for spherical tensors and yellow reddish colors for Cartesian type formulations. So it's just essentially a basis change in how you define types. And the physics community likes these spherical harmonics a lot. And so if we can now decompose any tensor into spherical tensors, we're looking for a basis of these spherical tensors. And it turns out that spherical harmonics form exactly a basis for, or you could use the spherical harmonics to form a basis of the space of spherical tensors. And this is why you encounter spherical harmonics in a lot of these applications. And besides being the underlying basis for spherical tensors, they also have a lot of other very nice properties. So any function on the sphere can be decomposed into a linear combination of the spherical harmonics. They also represent molecular orbitals for the hydrogen atom because you have spherical symmetry, and a couple of other nice properties. But for us, the important thing is that they're the Lego blocks of all possible types we can build, all possible types for 3D rotations, that is. And so tensor field networks is an architecture that now uses these types, these spherical harmonics-based types, spherical types, as the underlying features for accounting. And so because you have many of them, you now see many kind of message arrows. So you get an L0 message, an L1 message, an L2 message, and so on, up to a max L that you specify in the architecture. And in practice, people usually don't go beyond L equal to 2, because some of these operations tend to be pretty computationally intensive to compute. But there are examples of networks that implicitly go up to L11, and in some other applications in astronomy, they actually do go up to L equal 1,000. And intuitively, you can think of higher L degrees. So if you have this functional view of spherical harmonics, or if you look at them here, as resolving more angular degrees of freedom, more angular, giving you more angular resolution. So if you have a higher order L, you'll be able to disentangle things that are close by in angle space from a given vantage point. Now, I've got multiple messages, L1, L0, L1, L2, L3, and so on. And then there are defined multiplication rules for these spherical tensors, where I know exactly if I multiply something of type L equal 1 with something of type L equal 2, I have possibilities to get out something that's L equal to 3, L equal to 2, and L equal to 1. So you always get up to the sum of the L terms and down to the absolute difference, so the absolute value of the difference. So if I had a 2 and an L equal 2 and L equal 2 feature, I'd be able to get features out that are L4, 3, 2, 1, and 0. And so these multiplication rules are known as the Clebsch-Gordon tensor product, or the Clebsch-Gordon coefficients, because those coefficients would just be 0 for any other types. So people in machine learning tend to call these Clebsch-Gordon tensor product. And that's what this new symbol here is that has the little x here. And what I can do now is I can, for each of these tensor product paths, right, which would be a combination of L2, L3, and whatever thing goes into the L4 channel. So if I take the L2, L3, and the output L4, I can assign that a unique weight, because that will not mix different types. And so for all of those different paths, I can now give out different weights, and I can thereby parameterize this Clebsch-Gordon tensor product. And that's why you see a little W here. So this is a weight matrix that actually parameterizes the tensor product. And so the message at any given time would be a parameterized version of the tensor product of all the different types at the input, combined with, in spherical harmonics, in tensor field networks, I take the position vector, so the vector pointing from node I to node J, and I embed it with the spherical harmonics. So I use spherical harmonic 0, which will give me a scalar. I use spherical harmonic 1 and apply it to this distance vector, and that'll give me a vector. I'll use spherical harmonic 2, or all 5 of them, essentially, to get the 5 components of the L equal 2 tensor, spherical tensor, and that will give me an L2 tensor. And so I create those tensor products with all of the different projections on spherical harmonics of the distance vector. And that's how I define my message. And then the rest is just as normal in geometric GNNs. You would just have an aggregation step, which often is sum aggregation or mean aggregation. And then you would proceed doing the next thing. So you would get updated features in all of your channels, L0, 1, 2, 3, however high you go in L order. You would again compute the projections of your distances, and you'd perform all the different paths, now with different weights because you're in the second layer. And then you'd aggregate and update. And this is all the magic between tensor field networks. If you read the paper, you'll see the math looks much more complicated than what actually happens if you understand the basic idea. There's essentially nothing else but doing these projections of the spherical harmonics to get you these features, and then doing the different tensor product components. And one thing I've left out here is that the spherical harmonic depends on the orientation, but what we also have is the distance of that vector as well, right? And so because with spherical harmonics, we've sharded everything into essentially angular space, I can give out different weights based on different distances. And this is what happens here. So you would usually, your weights would actually be, you would bin, for example, your distances into 16 bins, 16 distance bins, around 16 different reference positions, reference distances. So 1 angstrom, 2 angstrom, 3 angstrom, and so on. The bond between two atoms typically tends to be on the order of 1 to 2 angstrom. And then you would assign weights for those different distance bins. And that's it. You have now essentially understood the key idea behind tensor field networks and any of these other higher order equivariant networks. And the key idea to always bear in mind, where is it? The key idea to always bear in mind is that we're essentially just doing accounting, and the geometric features we work with have just become more complicated. And the multiplication and addition rules have just become more complicated. But fundamentally, this is still exactly what we're doing. Now, one brief word on essentially Mason, the atomic cluster expansion, and on higher order terms. How can you use this now in order to dynamically create these high body orders that I mentioned at the beginning, right? Like dihedral type angles and so on. There is a very neat trick that is called the atomic density trick. And ultimately, it's just the binomial formula or the n-nomial formula. And so if I want to create features, interactions of the type x1, x2, x3, x4, x5, so that would be something like x to the power 5, I could individually compute all of those, which we've already said is scales exponentially in the number of, in the multiplicity of the order that I want as body order. Or what I could do instead is I could first sum up 10 different nodes, and then I could take this particular combination to the power of 2. So if I square a plus b, I'll get terms out that are a squared, ab, and b squared. But I've only done one multiplication. So if I wanted a squared, ab, and b squared, I would need to do 3 multiplications, aa, ab, bb. But if I do a plus b,